Eu já não tenho vídeo por causa disso. Daí a gente aproveita que você tá aqui, você já vai fazer as coisas também.
Check, check, check. This is microphone check for the stream. Check, 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 check. 1, 2, 1, 2. Hey, hey. Check, check, check.
Depois a gente deixa uma cópia aqui.
Eu achei que vocês tinham falado aquele dia que tinha que ir embora junto com as coisas. Mas não, vocês fizeram importação separada.
A gente fez a importação separada. Mas o nosso equipamento veio embora. Ah, ele tava demorando tanto. Yeah, so I have to test if this is good, so that doesn't work. Sometimes, you know, you think it's good and then everything goes away. Yeah, can you just, if you don't mind? No, but I also. This doesn't keep good. There's one slide. I can survive if you try.
So are you putting it under this?
I just put it on the desktop. Yeah. It's not opening automatically.
Podemos trocar?
Você quer que a gente comece depois da...
Não. Não, você já começa depois do break.
Isso.
Você e o Scott. E o Tércio e o Medioso passam para depois. Ah, ok.
Meleti told me that you asked to be this section. No, no, no. It's fine with you. That was far. Okay.
Well, that's should be these the green, no, the one for left. Click on this one. Then adjust.
Yeah, I'll go with
Thanks a lot.
Yeah, first you should sit there.
Because if you sit there, yeah, you can sit. Yeah.
Thank you.
I only think that for the four of you to stay there, you have to stay over this side and over the other side, not to be in the way of the screen. But it's fine. Okay. So we keep the way it is. Like that? Yeah, I think that you can sit there and because if you sit in this side, you won't be in the way of the screen. Because if you sit there, you can. Okay.
Is this one?
Or the version 5.
Então tá tudo bem?
Tá tudo bem.
O Michoto vai ficar sentado o tempo todo.
Vai avisar.
You stay here or stay there. Okay.
So you're gonna be the first one.
No, he is the first one. He's the first one. Yeah. Oh, right, this is
Sí, sí. It's here because people stay here for presentations. And that's the only stage.
I suppose to. Strange, but I don't know what I hear.
Also, after all that, they go out and next to us, get everybody from 5 minutes down to a minute and a half. You well, if it gets accepted, we'll figure that out.
Not a period. Coordinating, right?
the hallway
To the left.
on your right. Go left and then that's the hallway right. You should go here.
Go to the left.
And then the end of the
How do I
row.
get to this place?
Yeah. And then when you come back, the door will be open. Eu deixaria já a sua.
Ele já tá ali. Ah, já deixaria ali. Porque não, né? Obrigado.
Acho que aqui é bom. Eu vou mostrar. Tá do outro lado.
Seria bom.
Não consigo sair.
Seria bom se aparecer aquilo ali atrás.
A gente já filmou os dois.
Bom, ficou melhor. Se eu quiser mudar isso.
Ó, aí se eu ficar lá, não dá. A gente fez um com cada banner.
Pra aproveitar os fundos e mostrar. Não, a pessoa não.
You are still young. Look at me. Lucky you. Yeah. No, it's not that because I drink a lot of red wine.
sei que é o mais importante.
Agora chamei as pessoas. Ele é mal educado.
Hello. Well, we are about to start the second session. Please, come in. Well, before starting, I have some announcements for the Brazilian contingent that are here. Please start talking either to me, Regina, or Marcelo about getting signed the per diem and getting reimbursement for your tickets. Please do that. We want to do that here before you go back home, because if you don't get it here, you're not going to get paid. Well, we will start now the second session of this morning, and we'll start with Tercio Ambrisi and Carlos Roberto Metioso that will talk about multi-scale process driving tropical convection and influence of the aerosol. Please, Tercio, you will start?
Yes.
Okay.
Okay, good morning, everyone. Hope you have a good breakfast or coffee break. Okay, what Roberto and I have proposed is quite interesting. In fact, we are going to show you some large-scale influence on the Amazon region, because if we want to understand how the Amazon is responding to aerosols and how the convection actually is having an important role for the other parts of the South America, and particularly over Brazil, we have to understand how the large-scale influence is going to have an impact over there. So what we're going to show you here, it's some of the research, ongoing research that try to understand a little bit better the convection of the Amazon region and how we are going to tackle that in terms of models. Okay, so the long-term goal of our project is to develop constraints on model parameterizations for tropical rainforests and to assess how these constraints are perturbed by pollution. So the project is going to address the fundamental process that drive tropical deep convection and the aerosol effects on this process. We are going to do that in two ways. One is through a statistical analysis of the data from the Gulf Amazon, and also to study and understand the atmospheric large-scale environment that is relevant for the convection and the interaction. and also we are going to use a collective of models going from the general circulation models up to the cloud resolving models. Okay. So our team, it's from the University of São Paulo. We have three researchers from there. Also, we have some contributions from other institutes in Brazil, and one researcher from the University of Vigo from Spain. And we also have the UCLA team, Professor Mechoso, David Nealing, and some graduate students, and also Dr. Ruby Land from PNNL. Okay, some of the research to trying to understand a little bit better what's going on the Amazon region before we go to the data itself. Here it's quite interesting. This is a paper just published at HES, and what we did was to try to understand better how the Amazon plays a role in the hydrological budget. And what we run was the Lagrangian moisture tracking scheme. It's quite interesting because you can analyze the moisture 10 days before, where is the source, and also we can analyze the moistures 10 days afterwards, which is the sink. So what I'm going to show you here first is the backwards analysis for the soil moisture over the Amazon, over this region here, for February, March, April, May. Here is actually the middle to the end of the rain season in Brazil, the monsoon season, and the March, April, May is quite important for the rain season in the north and northeast Brazil particularly. So the red one here is the source, and the blue is the sink. So we have the source over here, sink over here, and as we can see here for February, March, April, the tropical North Atlantic actually is the source of the humidity that comes to the Amazon region, and it gets weak as you go along of the season. And the sink of the moisture actually is over the southeast of Brazil during this period. Another thing we did was to analyze this moisture source during the flood and drought years over the Amazon region. Here are the years for the floods, here are the years for the drought, and the green means source intensified in the flood years, pink source intensified in the drought years. Again, I have the moisture source over here, the sink of moisture over this side here. So as you can see, for the flood years, actually the source are in the tropical North Atlantic over here, and some here in the South Atlantic. But as and the pink one, the drought years, the most important thing is here over the tropical South Atlantic source. So we can have actually a clear idea as source or sink what's going to happen during this period here. For instance, you see that for the drought years, the impact is going to be here in the south of Brazil, southeast of South America. And we also did some analysis considering the ENSO years. For this side here, for the green now is for La Nina, for the pink is for El Nino. Again, moisture, sinks, and for the green, look that for La Nina is the tropical North Atlantic, that is the source of the moisture that comes to the Amazon region, and for the El Nino, actually is the South Atlantic, so you don't have so much over there. And as we would expect it, during El Nino we have more precipitation or over the south of Brazil, and during La Nina it's more to the southeast of Brazil. So we also did some analysis using different global and regional models. We are showing here, this is for a square box over the Amazon region, just considering the reference period, and the black here is the CRU data. This is precipitation millimeters per day, and what we did was to analyze how the models perform in terms of the seasonal variability of the precipitation, and also how the future scenarios is going to show to us. So in general, all the models shows negative precipitation over the Amazon region for the end of the 21st century. And it's interesting, the regional models actually produce a much closer precipitation cycle over this region here. Yeah. We also are trying to, we are analyzing how the resolution of the models are important to represent the precipitation or even the temperature over South America, but in particular over the Amazon region. And sometimes this figure is not too good. I think it's because the light is on. Yeah, but what we can see that's of course when we increase the resolution, we represent a little bit better the reality, let's say, and that's the point. I mean, how depend on how the clouds are going to be represented in the models. And how we are going to increase our resolution, we have to change the parameters. We have to have a more specific parameterization of these clouds. So in the interaction with the aerosol is going to be important. And we also separated dry periods and wet periods of the Amazon region and how the models performs on that. As you can see, sometimes the streams are superestimated by the models, and the drought period or the dry season is less simulated. So we also decide to analyze how the mesoscale convective systems are acting over the Amazon region. That's quite important, since we are making lots of measures of data over there. We want to understand the clouds over there. So I just start with MSc students that the goal is to characterize the convective activity of the continental and oceanic mesoscale convective systems, particularly during the Go Amazon region, and try to understand these characteristics. So what we are going to do is to evaluate the spatial distribution, diurnal variability, life cycle displacement, and others, evaluate the dynamic and thermodynamic conditions observed during the genesis and evolution of the MCS life cycle, and also to characterize the synoptic conditions with attention to the identifications of preconditioning and triggering the mechanisms convection. And we have already done some calculations. We got the data from 18 February up to 26th of March. Here is the time of the beginning of the systems, the life cycle, the position. What we are doing, we are using the foretrack, which is the forecasting and tracking the evolution of cloud systems, which was developed by Dr. Luis Machado, and it used satellite data to do this. As an example, this is for what happened during that period from end of February to the end of March. These are the systems, the direction of these systems. You can really tracking the systems quite closely. And for that period, for instance, we've got the frequency of occurrence was systems with less than 3 hours of life, some with 3 and 6, and some bigger than 6 hours. And this is also interesting because it's the evolution of the area of this MSS along of the year. Along of the day, sorry. So for future work, one question linked also to the aerosols and the pollution is what is the impact of the vehicular emissions around Manaus and the air quality. We saw here before that can see the plume going out from the city. So what we are going to do is to run the WRF chemistry model and try to simulate all the gases that is going to produce by the vehicles over the Amazon. In fact, in Manaus, it seems that we've got 600,000 vehicles, 50% of automobiles, 20 trucks, 1.8 buses, and 23% of motorcycles. No? So this is actually to show you the emissions of CO over the Amazon region and how is going. The plume is going to the west over here, and we are going to use all these regions to simulate it. And we just got a postdoc that is going to use the HADGEN family and the UCLA atmospheric models, try actually to analyze how these models are performing in terms of resolution and also how they can use the surface flux analysis to better represent the simulations. So finally, the benefits of US and Brazil collaboration. In fact, the UCLA and their group has large experience on general circulation models, particularly with emphasis on the coupled atmosphere models. At the USP, we have large experience on regional climate models. So the idea is we can transfer this knowledge to each other, and also we have planned from the senior scientists to go to UCLA and the UCLA scientists to come to USP for short courses and seminars, and to increase these interactions between our institutions. Particularly next semesters, Professor Roberto is going to give a course of 1 or 2 weeks at São Paulo, University of São Paulo. So said that, I think I'm going to pass on to Roberto.
Thank you, Tessia. In case you have been wondering why I have been sitting here, it's not because I like the limelight as everybody, but because I have to go backstage to come onto the podium. Okay, the first 2 slides of this my presentation were to repeat the members or the team members, and this was very well covered by Tercio already. And so I'm going straight to our part and what we are doing also in collaboration with the Pacific Northwest National Laboratory. So the goal, our primary goal, is to improve the parameterizations of clouds and aerosol effects in climate models. And for that, we will use Go Amazon data very much and model output from different models that will be selected. At this moment, to start with, the project we are focusing on convective onset. That means when is that convection starts, when it rains starts. And we anticipate that we have learned some things about this problem from analysis of other arm sites. But we anticipate that the tropical site, the Go Amazon site, will bring very interesting information on tropical lands. Okay, so no, I don't have to preach to the converter, but you are all very much aware that the simulation of the rainfall by in the, say, monsoon season, January, December, January, February, by the models. These are the models that participate in IPCC. And if you look at the bottom right, is some estimate of the observed, whereas all of the other ones are simulations. And there are very, very few of these models that really do a good job. And that means that the rainfall that is produced by the model itself, okay, has deficiency in several places. Now, that's easy to say, and now what is more difficult is to see how can we cure this problem. So let's go more into the processes, and here is a schematic of what happens in the cloud, in convection, in deep convection, And several of these processes, you do have to represent them with equations in these codes of the models. So for example, there is mixing. Of course, this is the boundary layer, the layer closer to the ground. Now there is mixing of air from the boundary layer into the cloud. The cloud, as it grows, entrains air from different places. You can see here from above and also from below. So increased air entrains air with moisture, and that itself is going to provide a source of buoyancy for the air to continue going up. The microphysics will be influential because when there is the ice formation, then we will release heat, and that contributes to the activity of the plume, and so on and so forth. Okay, and there are different types of clouds, of course, at different heights. Now, to predict the climate impact or the role of the precipitation in the climate system, as well as, very importantly these days, to predict the distribution of tracers, and in particular how the aerosols move in the atmosphere, I mean, one has to be able to predict all of these changes in mass that are happening in the cloud. So our strategy has been to start from the Go Amazon data and look at a quantity that we have taken as an indicator of precipitation. And that was suggested by previous work on other arm sites. Okay, and I will show you in a minute how the column integrated water vapor, okay, that's a key quantity in my talk, is a good indicator of the rain. Okay? And then look for other indicators. And we anticipate that there are going to be other indicators because the site is more complicated, because of the diurnal cycle and all of these things that happen, as well as the aerosol. Once that we identify these indicators, and then we will test from the ideas that we get from this basic research on the new parameters of the parameterizations, then we will go to the climate models and we'll change the parameters, and we'll see how this influences the results. And you will see some hint of how this can happen. And I repeat, the goal is to improve the parameterizations of the cloud in other models. Here is these are two plots. One is from the tropical Western Pacific on the left. This on the left is for Nauru Island in the tropical Western Pacific. And this is for Go Amazon. And so we want to see if what we have learned from this site is okay for the Go Amazon site. And what is happening here is we have taken the soundings and taken the column water vapor that is in the entire column of the atmosphere, okay? And this is the average precipitation. So this is taken maybe before the precipitation starts, sometimes some period before the precipitation starts. And now we look at what the precipitation in millimeters per hour. And the key point in this figure is that there is like a pickup value of the column water vapor. So the column of the atmosphere has to be wet enough to precipitation starts. And when it starts, it goes. You know, you can see all of these three are much more precipitation than these ones. Okay, so relatively dry, and then increases, and then there is a pickup. Okay, then we went to Go Amazon. Now, mind you that this is a statistical analysis, and that he also talks about the need for sustained observations that Go Amazon live for a long time, so you can get data. And so therefore there are less observations, and it's more spotty. The plot is more there, but roughly, I mean, we can see similar behavior, that the precipitation is less for our let's say drier columns, and then it starts picking up. Okay, and I want to jump this. So our method is the following. So we are going to take the temperature of a sounding, given by a sounding, the vertical distribution of temperature given by a sounding. And then we will imagine that we start from the surface with a parcel of water, of air with water. And we leave the parcel to go up in the atmosphere. But we let it in a very simple framework. We start with a very simple framework. Nothing happens to these exchanges of water. There is no exchange of water at all. There is no interaction of the parcel with the environment. Okay, so we let it go up, and then we look at the difference between the two the reality that is a sounding that has everything, and the parcel that we sent that has nothing, just simply the parcel going up. And so that's it. This is what is plotted over here. It's the temperature difference between that parcel and the parcel and the actual sounding. Okay, so the actual sounding has everything, and each one of these lines is a very simple evolution of a parcel of air with water vapor. And now this difference is positive at all levels. That means that the what we call buoyancy, or the air has, as it goes up, will have everywhere it goes, it will have a warmer temperature than the actual temperature that we measure with the sounding, which means that all of these values of cloud water vapor will be such that it rains. Okay? And we just said that it doesn't rain for all of these values. So the cloud water, incidentally, the cloud water vapor is indicated by the colors, and these are the very high column water vapors where the precipitation has picked up according to the observations. And these are very relatively low values, the column water vapor, where there is no precipitation. So we have taken a very simple-minded approach, and we have said, okay, I mean, nothing happens to the parcel, just goes up and just thermodynamically interacts with the environment, then everything will be unstable and it will rain. Then we have tried put different algorithms inside. For example, in this one, we have included the mixing of these parcels as they go up in a way that is consistent with the way it's used in models, in the general circulation models. Plus, we have included, in a little bit idealized way, microphysics in the form of the melting, the freezing of the parcels, at this particular level. Okay? So we see a difference. Of course, it takes a little bit of time to look at these things. But if you look at the right, in the left, the difference is that after we put all these physics that we have done so far, these three curves that are the three most on the right here are the only ones that really rain. Okay. So what that is telling us that we need to include several of these processes, and by tuning the coefficients, by changing the coefficients in these processes, we can get the cloud water vapor values that are needed to rain, and then they rain. And you can imagine that we can do this exercise with also in different cases. We can stratify cases that are polluted and cases that are pristine. And in that case, we see the effect of the aerosol. Okay, now this is the result for Go Amazon. So it's not as spectacular as the other one. You can see that they are mostly the left to right variations in these curves are less in the Go Amazon side. But we expected that in a way, if we are right, because the boundary layer processes and other processes in the Amazon should be as important maybe as a cloud water vapor in the Amazon, in the framework of the Amazon. So our current research is we are looking for the processes that give us a behavior closer to the observed. And to see how this really can influence a climate model. Okay, here this is not for the Go Amazon. It's for some location in the intertropical Pacific. Okay, this is again the cloud water vapor here, and the observations are given by the satellite. And these are these curves that curve a little bit to the right. Okay? So we, according to what I said before, the more cloud water vapor there is, okay, it comes to a point where the precipitation starts happening. The interesting thing is that the other curves, these curves that unfortunately they end with a straight line, which I shouldn't really be emphasizing because this is a part that is not exactly right, but there are other things to look at. Okay, these other processes, these other curves, the colors are practically superimposed, are produced by a model, by one of the NCAR models, that is called 3.5, the version 3.5. And this was tuned to, with their previous research, on the Eastern Pacific was tuned to produce the right beams for precipitation. And you see that the model really, with this right for precipitation, the right tuning, then it really gets to the pickup. We get to the value, the right value at which we have cloud water vapor and picks up. Okay, so I'm finishing up, of course, I'm sorry for taking time. We have in PNNL our colleagues contributing to the study the role of aerosol. In the clean and polluted environments, they have taken, again, from the networks, they have taken the initial condition from clean and polluted networks, and they see that there is much more activity in the cloud when there are polluted networks. But in addition to that, the umbols, the so-called umbols, this big cloud at the top of the cloud is much bigger when there are aerosols. So, ending up, we expect at some point to look at the different influences of the processes around the world on the precipitation over the Amazon. Again, to kind of stratify cases and see if parameterizations are able to handle them. Okay, so convection, the big result that we have gotten so far in a few months into the project is that convection onset over tropical ocean and vegetated regions have both important similarities, but they have also complex differences. So, thank you.
Tercio, thank you, Mechoso. I would like to call now Enrique Barbosa and Scott Martin that will present the next paper.
Good morning, everyone. And my name is Enrique Barbosa. I'm from the University of São Paulo. And Scott and I will be talking to you today about our project. It's one of the funded Go Amazon projects. And it's actually a huge collaboration. It's my first 5 lines long title project. And it's the Brazil-USA Collaborative Research on Modifications by Anthropogenic Pollution of the Natural Atmospheric Chemistry and Particle Microphysics over the Amazon forest during the 2 IOPs. So it's within the scope of the funded projects, our collaboration is threefold. It's 3 parts. So in Brazil, we have funding from the FAPESP Foundation at the University of São Paulo. My colleague, Rodrigo Souza at FAPESP, he is from the University of the State of Amazonas, and Scott is from Harvard University and funded by DOE. So the goals, you have seen a lot of pictures already about the Go Amazon and the sites and everything. So the goals of our project is 2. First is to understand what are the factors affecting the particle size distributions of the region, especially focused on the effects of anthropogenic pollution. How does that mix up with the biogenic aerosols that you usually have in the region? And the second main goal is then to develop and implement an upscaling analysis from the previous knowledge that we hope to get on the possible climatic impacts of this present day and maybe future anthropogenic pollution in the region, in the tropics. So our proposal is then to really do the measurements specifically for the two IOPs, carry out the related data analysis. One of the IOPs are during the wet season. It's done. The second IOP just ended like 2 weeks ago. And these two IOPs are meant to coincide with the DOE G1 aircraft measurements, also the Chuva project from Luiz Augusto in the audience, and the Halo aircraft, which is a partnership between the Brazilians and the Germans. The three objectives of our project is then to understand these interactions between the biogenic aerosols and the anthropogenic pollution, specifically looking at possible shifts in the production of secondary organic aerosols, understand this mechanism of new particle production for both the natural and the polluted conditions over the tropical forest, and translate this knowledge into the upscales to climate. So these are the experimental sites. If we can have the lights in the front off, that's make a lot better. I don't know who's responsible for that. So T0 sites is a mixture of 3 sites. The Ato Tautau Observatory, Paulo already told us about that today, ZF2 and Embrapa site. And then we have these other sites inside the city and downwind. And to emphasize, this is a huge effort. These are some of the institutions directly taking care of these sites. While putting this together, I necessarily made many mistakes and forgot many things, so forgive me. And at our lab at the Physics Institute at the University of São Paulo, we are particularly responsible for this site, T2, Embrapa, part of the instrumentation of ZF2, and also helping our German colleagues at T0, all funded by FAPESP in our case. So we are doing many measurements in the scope of our project. I will not talk at all, not even about like 10% of what we have done so far. So I will focus mostly on the vertical profiles of the distribution of particles in the atmosphere done at 2 different sites across the river and like downwind and upwind, and also some cloud-related measurements, which is the size-resolved CCN measurements. So this is the Ato Tower. Paulo talked about that today. This is one of the 80-meter towers where I'm going to be showing some of the results. So this is the Embrapa site, upwind of Manaus. Some land use change, but it doesn't really matter because I'm mostly looking at remote sensing instruments from the ground to look into aerosols and clouds. And the T2 site just across the city of Manaus, which you could see here on the margin. That's like 5 or 6 kilometers on the other side. And so let's have a look at the vertical distribution of particles. So just to be sure that everybody understood, this is a particle backscatter coefficient in inverse megameters on this scale from 0 to 6 inverse megameters. This goes from ground level up to 4.5 kilometers up. Always in the top, it's going to be the Embrapa site, which is upwind, and downwind site here. If I can then make this work. So this is the whole second IOP of measurements. Embrapa site, we have clouds, some clean conditions on both sides, and aerosols, clouds forming inside the aerosol layer. This is all biomass burning aerosols, most of the cases. Again, some clean sites, polluted, and on the right is what's going into the panel. So each panel shows 24 hours. We are already on September 5th. We have some strong pollution cases, and when it precipitates, it cleans up the atmosphere. But the general message here is that the 2 sites look remarkably the same. And if I go back to my presentation, so at least from the ground measurements, these biomass burning transport aerosols are well confined in this biomass burning layer. If you look at the time difference between the two sites is about 1.5 hours, which is okay to the 30 kilometers distance that we have between the two sites. This particular event of very strong aerosol layer, it's actually, if you look at the ground, this is ACSM mass spectrometer measurement. So this is 30 micrograms of organic aerosols around the same time that you have that measurement on the vertical profile at both sides. This is another day, 27th of August. So upwind and downwind, we can see exactly the same structures. Yet another day, 30th of August. So lots of precipitation in the previous day, clean up at both sides. And even here, if you look at the very small scales, these are present at both sides. So at least for the IOP number 2, during the biomass burning season, there is no clear signal of the Manaus plume, at least that we can clearly distinguish with our ground-based LiDAR measurements just across the river. So this means a very strong regional component that's somehow very complementary to what Paulo showed us today. Second set of measurements, and I picked up these two to be, well, not only different from what Paulo was showing up previously, but also because these are kind of important measurements for the modelers that have been showing their projects previously. So we have to know where is the aerosol in the column, and also this other measurement, which is how much of these aerosols can be converted into cloud droplets. So this is a setup at the Atto site, and this is another setup that we ran last year with some colleagues from the UK. And these are results from T3. So we took the system at Atto to T3 for comparison and calibration. When you look at, so this is the particle size diameter, and the first row is concentration, and lower is the hygroscopicity. So when we have lots of particles, we have low hygroscopicity around 0.1. When you have low background values, we have higher hygroscopicity. On average for that week, we had like 0.2, which is fairly low yet. Then we took the system to Atto, and that's the measurements that we have showing this. This is the first IOP, and there's too much details in the plot to discuss with you right now, but the upper panel is the size. We have kappa activated fraction, so most of the time we have it around 1. And the lower panel is the steepness of this activation curve. And on the average value is 0.21. So actually quite close to the previous. Of course, it's very limited time. We have to repeat the analysis for the whole data set, but still it's surprisingly alike. And these are in agreement with the measurements done with our UK colleagues last year. So if you look at different supersaturation levels, then you have a hygroscopicity ranging between like 0.15 and 0.25 for the different supersaturation levels. And last set of measurements, which unfortunately we don't have now for the Amazon. We're still trying to get one instrument to do that, as the before the crowd droplets, which means how much do water vapor is taken up by the aerosol particles. So this is just to show you this result. So this is ammonium sulfate in black, usually ammonium nitrate. So use it for calibration, and the dots are the measurements at different sizes. So very low water uptake. And these all at some point should go into the models and help our understanding of the whole picture. So having said that, I pass to Scott.
helpful. Oh, no, it's working. Thank you. Okay, the mouse got stuck for a minute. Okay, so I wanted to give you a perspective on what we're seeing from the aircraft data with respect to the plume. So this is the G1, which flew in the first IOP as well as the second IOP. First IOP, cleaner background conditions, and then the influence of the Manaus plume. And the second IOP, a mix of clean background conditions, biomass burning, and the plume. I'm going to focus today on the first IOP. Simply because those are the data that I've had a chance to really take a closer look at so far. Okay, so this is all of the flights from IOP 1. Here is Manaus, here is T2, here is T3, ZF2 is up here, ATO is over there. So you get a sense of the aircraft. The aircraft was forecasting with a model developed by Carlo Longo from IMPE, forecasting where the plume would go, and then we would try to follow it. So you can see the forecast generally had it going from east to west, though sometimes it was going in slightly different directions. And then we would pick up on the plume with the flight. We would adjust in real time and extend some of the legs as necessary in order to try to have the plume centered down the leg. So in some ways, these flight patterns then represent where the plume was across, I think there were a total of 16 flights in IOP 1, and we did do one background flight. Okay, so this is a perspective showing Manaus towards T3. This is a particular flight. That's what I'm going to focus on today. I selected one flight to go into depth with to give you a perspective on the types of things we're seeing from the aircraft. On this particular slide, I want to emphasize these lines. These are forward trajectories from Master IAG, which is Maria Assunção's group at University of São Paulo, has run forward trajectories. Each tick is about 50 minutes. This is two trajectories, one launched before this flight at 12 on UTC, one launched at 1800, and 4 altitudes. So you got a total of 8 lines, and you can see in approximately 3 hours, 1, 2, 3, 4, 4 ticks, you can see the plume is projected to basically be going in the direction we expect, and spreads out a bit depending on the initial altitudes. This is the aircraft. The selected data are all from the aircraft, running from 550 to 650 meters. So the aircraft is, for the shown data, is all at one altitude. And we're going to be looking at the data on this flight for the rest of the talk. Okay? All right. So, and we're going to be looking from this perspective for the rest of the talk. So this is the same plot, just rotated. So here's T1, here's T3, here those trajectories are, here's the flight path, and every other slide we show will be from this trajectory. All right, so the first question is the plume. There ought to be a lot of particles. Okay, so this is the number of particles per cubic centimeter. You can see out on the edges, this is the actual profile here. You can't read the numbers, but out on the edges, wet season, these numbers are in order 200-300 per cubic centimeter. In the plume, these numbers are going to 10,000, 20,000. And so you can see here comes the plume, here comes the plume, here comes the plume. This one is quite coincident with hitting the ground site, okay? And the broader plume fanning out, and you can see the well-constrained edges. This you will see is from a local, we believe the data add up. This is, even though it's wet season, this is, you'll see a peak several times. It really stands out in carbon monoxide. I'm not going to show you the carbon monoxide plot. A biomass burning, so I think there's a fire over here. We need to look that up still and see if the satellite can pick out a fire. But this peak I think is a fire, and then these are the plumes. And there are also brick kilns along here. That don't show up strongly in any identifiable features like this, but maybe they're responsible for something small like these guys here. Okay, so all right, so here we are crossing. So here's the plume, here's the plume, here's the plume as we go downwind, downwind, downwind. I'm going to talk in this talk mostly about particles and chemistry. The aircraft was outfitted with lots of chemistry instrumentation and lots of cloud microphysics instrumentation. And we'll hear in Jay Wang's talk and Luis Machado's talk more about the cloud side of the flights. I'm focusing on the aerosol microphysics. Okay, so in that regard, the plants are emitting a number of compounds, isoprene, C5H8, dimer of that, C10H16, trimer of that, C15H24. These things are rich in chemistry. This is what plants are putting out. These are kind of the perfumes that people like to smell, but they're also things used for signaling agents for insects. They're also things that plants will emit to try to attract a herbivore when they're being attacked by other species. These are things that might just leak out from the plants. There's also a rich photochemistry environment. Lots of sunlight leads to lots of OH radicals. These OH radicals attack these molecules. Ozone also gets produced. They attack these molecules. So when you start adding oxygen into these molecules, they go to lower vapor pressure. A fraction of those molecules then with the lower vapor pressure end up in the particle phase. These are the things that are serving as the cloud condensation nuclei for clouds to form, and in some clouds for rainfall to subsequently occur. So we're interested in how this type of cycle, this photochemical cycle from emissions from plants, atmospheric oxidation, particle formation, how that might be susceptible to the things that are in the plume, the anthropogenic pollution. All right, and so in particular, not to show you too much detailed chemistry, but to tell you if you start with one of those molecules I showed you, like isoprene or the terpenes, they become an activated radical species, and you end up with this peroxy radical. This peroxy radical is important because under natural conditions, it can go to things like carboxylic acids and hydroperoxides, where under polluted conditions, NO, NO2, it can make a host of different products. So I had to show you this chemistry slide so that you understand that within the chemical mechanism, clean conditions give you different products from polluted conditions, NO, NO2. They regulate whether you go from pathway 1 versus pathway 2. And so we have expectations for much different chemistry that leads to much different particles. So here's the pollution. Here's NO. Here you can see the NO plume coming down. There it is. Gets down to T2. Here's the biomass burning. There's also NO2 that looks similar, though I'm not showing it here. But you get the idea that there are large concentrations of NO in the plume and that those go down as you go downstream. Some of that goes into nitrates in particles. Some of that goes dry deposition to surfaces. Some of that gets incorporated into gas phase organic molecules. So they're kind of two sets of dominant molecules. Clean conditions, things like the methyl tetrols. This was a science paper from the Amazon about on order of 10 years ago, versus things like MVK methacrylin under polluted conditions, the NO pathway, HO2 pathway. So more pollution gives you faster photochemistry, gives you less isoprene, more of these other products, changes the ratio of MVK to methacrylin to isoprene, and the concentration of peroxides go up. So there's this whole train of event in the chemistry that occurs when we're in the NO plume. I think you need to know this much in order to know what's coming in the next couple of slides. Okay, so here's isoprene, and there's an isoprene hole. Okay, there's an isoprene hole here, here, here. You see the isoprene concentrations going down, going down, going down. You have isoprene, background emissions from all of the plants all over the place. In the increased photochemical cycle, because of the oxides of nitrogen, you have a lot more OH radicals on order of 10 times higher, and they're consuming the isoprene. So the isoprene is going away. At the same time, the first generation products, MVK, methacrylin, are also reacting away faster. You get this hole through the plume. You see there are a lot of other rich things. So we'll be bringing, as we continue the project, modeling tools, WRF-Chem, to the topic in order to understand the details, or try to understand the details within this plume. But you can see it's standing out in the raw data, which is always a good place to start when you are going to do a modeling exercise. Okay. Besides the isoprene coming out everywhere, you've also got anthropogenic VOCs, gasoline, and also industry. So here's toluene. Here's a big one. So you can see toluene is a great tracer for the plume. And it's also undergoing photochemical reaction. And so when that's taking place, so the isoprene, of course, starts from a large background and you're subtracting, whereas the toluene starts from 0 and you're adding. And so it's a lot easier to see. Acetone, you can see a peak. Also, you can see a peak in acetaldehyde. Acetone and acetaldehyde are also photochemical products of general VOC chemistry, both from anthropogenics and from terpenes. You can see those showing up in the plume. So we have a very rich data set coming out of this aircraft activity in order to start to think deeply about the processes that are taking place. Now, we wanted to couple that over to particle formation. So here's the organic particle, and you can see then there are peaks. Okay. To what extent is that secondary organic material that's produced by this VOC chemistry? To what extent is that associated with primary emissions of material from the city? We'll start to try to dissect that with the WRF-Chem modeling exercise. But you can see it again in the raw data, this strong effect of the plume downwind of Manaus. Here's sulfate. So we heard from Paulo Artacho, the oxidation of SO2. You see it showing up in the sulfate. Sulfate is more and more and more as you go downwind. The SO2 was less and less and less. Particle phase nitrate. I told you the NO from the gas phase is getting converted to various things, including particle phase nitrate. So you see that in the plume. I should emphasize there's not very much sulfate and nitrate on an absolute scale, but it's mostly organic, 90% organic on an absolute scale. But on a relative scale, you can see strong elevations of sulfate and nitrate in the plume, which has strong implications for the hygroscopic nature of the particles, including their activity as CCN. So that's kind of the one view through one flight of the aircraft data set to give you a sense of where we are and where we're going and why we're excited about what the data we've collected so far. Taking that back into context, isoprene, Amazonia is a huge hotspot globally, both in the wet season and in the dry season. And in particular, as we're thinking about the Amazon basin in transition, going back to several of the talks from today, one of the other things we're thinking about is the photochemical oxidant cycle and particle production. How is that changing under current conditions downwind of Manaus, possible future conditions, meaning greater economic development in the Amazonian basin, and possible kind of external global climate forcing on Amazonia. And with that, I conclude. Thank you for your attention.
Well, I invite Tercio and Enrique, please. We are running a bit late, so I'll open for 2 or 3 quick questions and quick answers. Questions? Well, if no questions, you guys were so clear that...
Can we go to lunch?
I think that they want to go to lunch.
Stay for lunch.
Okay, if we have no questions, let's go for lunch. Thank you very much. Oh, who? Oh, please, please.
The only parameter so far it has been the production of ice that we have interpreted according to some parameterization. Yes, and the hope is that with this, the second part I show with the WRF-Chem and the results with WRF-Chem, we will go into now with these results and analyze a more complex situation.
Please, Emilio.
I was curious, so far I haven't heard that any of the drawings on experiments have taken into account the growing proportion of the region and the state of secondary succession force. So to what extent is the modeling or the slice of the experiments are looking to see if there is a significant difference in these processes, whether you're looking over an area of relatively intact soils versus the secondary.
So, all right, so the original scope of the Go Amazon proposal, we also were going to look on the southern edge where this was one of the issues. With the resources that were available, we were really only able to focus on the Manaus area, where the issues of deforestation and reforestation are much less than in Hondonia and other parts. So I would say that is, so it's a very good question. I would say that's unfortunately, it was part of our proposal, unfortunately out of scope.
All right, so let's go for lunch. Lunch is ready for us. Thank you very much for a nice session.